Hi, everyone. Thank you, Adrian, for the invitation. It's a pleasure to tell you about results of our work. And let me start by acknowledging younger people who really did the work that I'm presenting today, in particular, Chris Sells, who is currently at postdoc at Harvard, but is moving to NYU in the fall to start his own group. Annabelle, who is currently in TU Munich, but is coming as a postdoc to ITAMP, and Fabian, Fabian Grust, who was in TU Munich, now moved to LMU, and that's the junior faculty member, and Michael Knapp, who is also, I guess, is no longer young assistant professor, kind of early career assistant professor in TU, and also what made this work very exciting was collaboration with people outside of sort of our conventional condensed matter theory community. So first of all, experimental groups by Manuel Bloch and Markus Greiner, and also colleagues from Harvard Medical School. So let me just give a brief outline. My talk will consist of two parts, which are somewhat independent, but you will see that both of them sort of bring together new tools of quantum simulation, quantum computing, and classical machine learning. In both cases, it's a combination of two ideas that are important for the success. And in the first case, we'll talk about quantum-assisted NMR inference, in particular, how we can use quantum simulators to do interpretation of NMR spectrum in the context of, especially in application to metabolomics. If you don't know what metabolomics is, don't worry. I didn't know about this myself until a few months ago when our colleagues started asking us about possible applications of quantum technology to this problem. And then the second part of my talk will be perhaps more familiar playground of quantum simulations, and this will be a discussion of recent experiments and recent ideas of what we can do in order to get new insights into strongly correlated systems using quantum gas microscopes. Okay, so as introduction, let me just point out that obviously we all have seen a lot of news about quantum technologies in the last few months or even years, and some of them will be overly optimistic. Say some of the early predictions said that quantum computers will develop so fast that by 2014 they will do computations faster than the entire universe. Then still a lot of kind of optimism is in the double exponential prediction of Hartmut-Neven, who says, well, the number of qubits should grow exponentially, and since Hilbert space grows exponentially with the number of qubits, so we should have the growth of Hilbert space, which is double exponential in time. Then there are sort of more cautious predictions, say by Gambetta, which says, well, actually, we shouldn't just talk about worry about number of qubits. We also should include sort of the coherence time, how well we can do our qubits. And what is interesting is that this excitement is no longer confined just to academia. Industry is really very excited about this. So you can see how much money people have been putting into quantum technologies. And so this is just money invested in quantum startups. So this is not just companies with a couple of graduate students. These are serious in companies with hundreds of millions, worth hundreds of millions of dollars. Of course, many of us think that, well, it's probably just another incarnation of a typical hype cycle where we will go through the peak of inflated expectations to arrive at the disillusionment. But I think it's a fair question to ask, well, so what what will be the outcome? So what are the actual technologies that, let's say, society in general will get from quantum revolution? And if you think about it, well, there are several very interesting ideas, right, which goes back to the first factorization of 15 using liquid NMR by Levin van der Sijven and company, and to more kind of recent developments, say a demonstration of quantum supremacy by Google, or variational estimation of the energy of a water molecule using ion chains. But say to a kind of audience outside of the physics communities, it's perhaps difficult to relate to these problems, right? They're still sort of very specialized, really addressed to kind of insiders audience. And this is why I think a major part of the challenge for quantum technologies now is to come up with ideas of practical applications of sort of quantum hardware that will be available in the near future. And it will not be perfect, it will be noisy, and it's not infinitely powerful. It will only have 50 or 100 qubits. So, and this was, let's say, emphasized by John Praskell when he coined this term noise intermediate scale quantum technology. And one of the interesting things which he also pointed out was that perhaps the most promising direction in which this kind of NISQ technology can be applied is for solving problems which are intrinsically quantum, that rely on quantum entanglement. In fact, so this comment even got a rating, not bullshit, if some of you know that there is this, I guess this Twitter account, right, which comments on quite a few ideas in quantum computing. It's actually not easy to get a rating of not bullshit from them. Anyway, so in the first part of my talk, I want to suggest one specific idea for this NISQ technology for quantum quantum hardware that we can have in the labs now, and that will be improved in the next few years for solving real-world problems. And this is specifically interpretation of NMR spectra. So, and you can already see this kind of in a nutshell what the problem is going to be. So we get a measurement of the NMR spectra, and we want to understand what is the system, what's the quantum system that underlies this spectrum. And as you will see, to make progress in this task, we will have to bring together three tools. So it's quantum simulation, quantum computing, and classical data science. So it's really the combination of the three which makes it possible to achieve this goal. So this is the kind of the outline of like just this first part. So first of all, I'll say a few words about what is what's the problem of NMR inference, like what's the field of metabolomics. Then I'll talk about how we can use sort of quantum hardware to help us with this inference. And particularly, you'll see that our idea relies on the application of a hybrid classical quantum algorithm. And then I'll comment on actually what are the machine learning parts of the problem. So that actually we cannot just do this procedure very naively. In fact, quite a few steps are involved in in this inference loop, steps involving just classical machine learning. And I'll say just a few words about actual implementation of this NMR inference. And many of the results of what I'll be talking about today already can be found in these two papers. Okay, so what is metabolomics? Well, basically, it's a study of small molecules which are involved in supporting the living cycle of cells. right? And it's a it's a broad range of molecules, which includes amino acids, like lipids, basically. Let's say carbohydrates, and it's like, so metabolomics is, let's say this, it's something which is useful for both medical research, say, even though it's a new field, it has already had a strong impact, say, on a variety of medical fields, say, in this different types of cancer, cardiovascular diseases, say, analysis of I think kidney diseases, but also just for kind of understanding how, let's say, food is processed in normal organisms. Let's say how bodies can handle like physical exercise. So that's all kind of, these are all fields in which metabolomics plays a major role. And let's say, just to give you some concrete example, like caffeine, right? Something we can all relate to, without which many of us cannot do physics. Well, it actually caffeine is metabolized into 3 specific metabolites. And so you would imagine that given the importance of these kind of these small molecules for for the operation of a human body, then by now we would have a full understanding and full characterization of all small molecules relevant to humans. Well, actually, this is not the case. And in fact, I was kind of amused to know that in the medical field, they also have a term, dark matter. So as physicists, we think that we own this term dark matter, but it turns out that only a tiny fraction of actual small molecule of the small molecules metabolites relevant to life, to humans, are characterized, and the rest, kind of, which are known to exist but have not been characterized yet, is what is called metabolic dark matter. So let me just give you kind of a rough number, which I found in this paper by Markley. So they estimate that the number of relevant metabolites is at least 200,000. However, at the moment, only 2,000 of them have been identified. So you can see it's just 1%. And if we talk about the number of, the number of metabolites that are used for for targeted profiling, this is even smaller. And so the 2 major techniques for identifying metabolites is mass spectroscopy and NMR. And in principle, NMR would be a much more powerful tool, right? Because you can do it in vivo, right? Because many of these metabolites may be extremely fragile, right? If you take them out of the body, and that's what you have to do if you want to do mass spectroscopy, then you destroy them. Also, mass spectroscopy gives you very limited information. Basically, from mass spectroscopy, you can reconstruct which atoms you have, right? But you don't really know in which order they are combined in a molecule. And in organic chemistry, you just interchange the position of 2 radicals, right? And you get a completely different molecule with completely different functions. And a major problem for actually kind of broader use of NMR is actually the challenge of going from the spectrum, from the measured NMR spectrum to the actual chemical compound. So maybe for people who sort of have not taken, who did not have this as part of the introductory quantum mechanics, let me just remind you what NMR is. So it's like a very kind of broad brushstroke picture. So if you think about, let's talk about, let's say, hydrogen NMR. So we think about protons. So this has been one half particle in a magnetic field. They split in like according to Zeeman splitting, a spin up and spin down states with a kind of characteristic energy difference. So this would be for an isolated proton. If we have hydrogens which are parts of a larger molecule, of course, we have very similar splitting. However, this splitting between up and down turns out to be not the same for hydrogen atoms which are part of a larger molecules compared to, let's say, just isolated protons. And the reason, there are several reasons for them. So the main one is, well, first of all, there is always some kind of screening by the environment, let's say diamagnetic response of carbon atoms, right? But furthermore, actually, there is interaction between the hydrogens. So as a result, there is an effective Hamiltonian which describes the spins of the protons, and it's actually accepted that the Hamiltonian, which one can use to describe the effective Hamiltonian of hydrogen spins, is Heisenberg type interaction between the spins and Zeeman coupling. So this Heisenberg interaction can be taken to be SU2 symmetric. Originally it has a large contribution from dipolar interaction, but because of averaging over configuration, one cannot take it to be, ends up being spin symmetric. But the Zeeman field is obviously just aligned with the direction of magnetic field. However, the kind of effective field experienced by every spin is different as a result of them, because they have different local environment. So as I said, our kind of major, like fundamental goal is, of course, to start on the spectrum and end up with the chemical composition. But as a physics problem, let us start with an intermediate scale problem, which already goes a long way, and ask the following question: given a spectrum, can we reconstruct the Hamiltonian? Can we reconstruct the effective spin Hamiltonian, which gives rise to the spectrum? So let me make several comments. So one thing you can worry about, well, is this problem even well defined? Do we have enough information, right, so that from the spectrum we can get all the parameters? So let us think about, so there are two aspects which are important to keep in mind. First of all, the ensemble over which we're averaging the spin Hamiltonian is infinite temperature. You can understand this just by observing that kind of the frequencies of NMR is is megahertz. So when we talk about scales, room temperature scales, we talk about temperatures like 3 orders of magnitude larger, right? So for practical purposes, we're really looking at like the occupation of all initial states are equally likely. And then therefore, essentially when we probe the spectrum, we're probing the entire many-body spectrum, and how many microscopic states do we have? Well, we have exponential number of states. So therefore, and of course, there are some kind of symmetry constraints, but then the result is still that the number of peaks that we can get, right? So the number of equations that we can get from the spectrum scales exponentially with the number of particles, whereas the number of variables in the spin, even though potentially we can have, all-to-all couplings, is polynomial. So therefore, the problem is always well defined. So you can also say, well, this is kind of reminiscent to something that mathematical physicists discussed a long time ago. There was an idea of whether you can reconstruct a drum, so whether you can hear the shape of a drum, right? So if you just have some linear system from the eigenmodes, whether you can reconstruct the underlying microscopic model. I want to point out that the quantum many-body system that we're looking at is very different, right? Because for linear systems, right, you just need to know if kind of a finite number of eigenfrequencies, and then the entire spectrum is just a superposition of this eigenstates, right? Whereas in a many-body state, like in an interacting system, we cannot break it into sort of like a combination of non-interacting degrees of freedom. So therefore, it is a much more challenging task. Okay, so how do we want to solve this? as I said previously, the idea is to actually use a hybrid algorithm. So that is something that has become popular in the last few days, and that combines implementing some kind of part of the procedure, let's say realizing a wave function on a quantum hardware, and then taking expectation values of the wave function of quantum hardware. And there have been applications of this in several fields, like in quantum chemistry, in high energy physics, in lattice gauge theory. But in this perspective, it's kind of natural to say, well, then if we want to understand something about the quantum system, such as this NMR spectrum, and the real challenge is that basically, naively at least, we have to solve the exponentially hard problem, right? Because we need to compute the spectrum, right? We need to get the spectral function, which involves all the states in our Hilbert space, and the number and the size of Hilbert space is exponential. So like doing it directly with classical computers is hard. Well, then why don't we do it on quantum hardware and quantum simulators, right? So we will simulate this, we will sort of start with some parameters, make a quantum system, make a quantum system that realizes a Hamiltonian with these particular values of interactions J, Zeeman field H, compute the spectrum, and then use classical procedure to optimize the parameter, because we want to match the spectrum that comes to us from experiments. So that is the idea of the hybrid algorithm. So the hard part, the kind of the exponentially challenging part of getting the spectrum will be done on a quantum computer, on a quantum simulator, whereas optimization will be done on a classical computer. Okay, so one suspicion you might have is, well, but somehow when we think about infinite temperature ensembles, it feels like it should be very classical, right? So the idea is that actually it's not true, that as soon as we start looking at, even though we start with an infinite temperature ensemble, but when we start looking at the correlation function, and basically you can show that an NMR spectrum can really be related to this specific time-dependent correlation function. So as soon as we apply an operator and we let it evolve, it immediately gets entangled. Like basically, this operator gets entangled with all other degrees with many degrees of freedom. And that's why we cannot use just simple classical calculations to compute the spectrum. Just let me give you a very simple example. Imagine we take a 4-spin particle, and then obviously for 4-spin, we can just, actually in this case, we use a Hamiltonian, which is, as you'll see, it's one of the molecules of the actual molecules of one of the metabolites relevant for sort of in medical research. So, and then you can just do simple classical Landau-Lifshitz. So what would the NMR spectrum look like? Well, it would be just this yellow line, right? You see this kind of broad peak. Then we can do slightly better. We can do truncated Wigner, which is putting some quantum mechanics at the semi-classical level. We would get this blue line. Right? Both of them are very different from the actual spectrum. So you really have to do the full quantum mechanical treatment to actually get the spectrum. And in fact, so this complexity of this procedure is something that has been studied, let's say, in the context of kind of the so-called DQC1, when you have one clean qubit model, which is interacting with a spin ensemble at infinite temperature. And it has been proven that it is actually, it can solve problems which are hard for classical computers, like say Shor and Jordan showed that it can be used to approximate the Jones polynomials, which cannot be done efficiently using classical algorithm. So, so this type of problems is, it's not equivalent to, say, universal quantum computing, but it is still hard and it cannot be simulated classically. Okay, so now, but how do we actually implement this? So Because the first idea that comes to mind is, well, if this is indeed the case, that we have to sample the entire Hilbert space, and we just said that it's exponentially large, it seems like we would have to work exponentially hard, even with quantum hardware, to compute the spectrum, because we would have to sample this exponential number of all initial states. Well, actually, this turns out to be not an issue. So we can, as you know, that if we take n particles, right, the total number of allowed values of total spin can take values which only scale linearly with the number of spins. And one can show, unfortunately, I do not have time to do this, that we can actually utilize this degeneracy to expedite the calculations. So basically, we don't really have to sample over all the states. We just have to take random states from different states with a certain total magnetization, right? And so out of this, and so the total number of sectors is n, right? And we have to sample, as it turns out, to be n times, just because like every quantum measurement, right, still gives you sort of, I remind you, like when you do a quantum measurement, we get a result which is not exactly the average, right? So there will always be fluctuations. So you can estimate, so how many measurements do you need to take so that the result converges to the average, which also turns out to be. And so altogether, turns out that we have to basically run the algorithm of the order of n squared times. So therefore, we can reduce the complexity from exponential to something which is polynomial, which just goes as n squared. So the simplest protocol that you can imagine, right, is that we do this sampling, right? So we prepare our initial ensembles with the corresponding probability. We evolve for time t. Then we measure, kind of the probability of states in a sector with a certain initial magnetization is proportional to magnetization, and that actually gives us a that what replaces this original SZ at time equals 0. And so then we just do evolution and measure a total SZ after the evolution, right? So therefore, it's really just start with initial state, evolve, measure total magnetization, and so you have to do n states, and you have to measure every one of them of the order of n times. And that gives us this kind of evolution function as a function of time. Then you do fast Fourier transform and you get your spectrum. So that is the simplest procedure. Well, actually, if there is one thing that quantum computers are good at, it's actually in taking Fourier transform. This is actually what makes Shor's factorization algorithm so efficient. So it turns out that one can make this whole procedure even more efficient. But to explain how this works, I have to introduce another idea, because one concern that you can have is, okay, we're trying to sample a thermal ensemble, but when we think about quantum computers, we're really thinking about purely coherent evolution, right? It's not that we start with the well-defined initial state. We do not prepare kind of thermal ensembles. So actually, we can use a trick which has been used quite extensively by people doing numerical calculations, and this is a trick based on purification. So for people who are not familiar with this trick, let me explain how it works. So let's say we have our physical space and we want to get to represent a certain density matrix. Say in the simplest case, it could be an infinite temperature density matrix. And so but we prefer to work with with the wave function. So the way to do it is to extend Hilbert space, right? So like say we basically make a precise copy of our physical Hilbert space, which we can call an ancilla. And now you can imagine, so taking a state in which we have exactly the same state for the physical space and for the ancilla space, right? And we sum over all of the states. Now, if we take a trace over the ancilla space, you can very easily see how we sum over this ancilla states, right? So then taking the trace, we keep on its diagonal term. So we end up again with a density matrix where we have identical states for the physical space, which is exactly infinite temperature ensemble. So so this state, right, is often called entangled pair state. And these states can be very efficiently created using quantum computers. So it turns out that basically you can start with a well-defined, say, initial state. You can see that also this is our physical system. This is our ancilla states. Then we just apply Adamar gate, which is basically sigma x operator. Then we do controlled knot. And so as a result of this operation, we have entangled pair state. Well, actually, in our case, we have, you remember, we have to start with something slightly more sophisticated, just because we're interested in measuring spin correlation functions. We want to start with a state which is not entirely just simple entangled pair state, but it also has the weights which are proportional to magnetization, total magnetization of the state. So it turns out that these states actually can also be generated by this trick, very similar to what I showed you here. So the only ingredient is that one has to add, like in addition to just physical system and like this copy, one has to introduce an extra ancilla bit and then use a kind of controlled operation with it. So let me not sort of, unless people are interested, I'll not really give you the detail, just to say, well, it's basically very similar procedure, can give us exactly the initial ensemble that we want. Okay, and so then, as we said, okay, so previously what we discussed was we just start with this initial state, right? And so then if we take a copy, trace of ancilla states, that will give us the initial space, and then so we can just evolve in time and get our overlaps as a function of time. But what we want is actually a Fourier transform of this wave function, right? So it's really, if we think about what we want to compute as a function, so this is our correlation function, target correlation function, a function of time, and then we need a Fourier transform of it. So how do you what will the actual kind of sequence of gates look like? So you can see that it will consist of now like this key element. So there is a physical system, and then there is a copy. So again, if you're not familiar with this quantum phase estimation, okay, details are not important. You can actually understand what it does just by thinking about what's happening here, right? You can see that because we're looking at evolution, so there is evolution of, there is a Bryan cat, right? So here you just have exponential, like the usual evolution operator, e to minus IHT, right? But on the brow, we have to apply e to IHT. So what's happening is that you see that our elements on like our actual physical states, they evolve with the evolution operator, e to minus IHT. But our ancillas, they evolve with this conjugate. So this really kind of mimics exactly this conjugate, this evolution of the bra states. So then you can see basically this is evolution, like for the first time step, this is evolution for the sort of twice the time step. So this is basically the solution operator square. And for the ancilla, it's of course conjugate squared and so on. And then we use this additional qubits, which actually do quantum phase estimation. So as a result, the output of this phase estimation circuit is that we measure the spectrum. So we basically get a kind of a binary number which encodes the spectrum. So as a result, we actually skip the step of doing Fourier transform classically, but rather the Fourier, we get the spectrum as a result of our evaluation of this quantum circuit. And you see that the price which we basically pay is quite minimal, that, okay, we have to double the number of qubits just to get an ancilla, and there will be also an extra log coming from the number of qubits that we have to add for doing the quantum phase estimation. Okay, so we can measure so given a Hamiltonian, right, a spin Hamiltonian, then we see how we can compute the spectrum efficiently using quantum hardware. But we still have to discuss how to solve actual optimization problem. So it turns out that this is not, it's not something you can do very directly. So if you think about the landscape, if you just start with a completely random Hamiltonian and try to optimize it, do steepest descent, trying to optimize parameters of the Hamiltonian, you will be stuck in some unphysical local minimum, and you will never come close to the Hamiltonian of the actual molecule. So it's a very rough landscape, optimization landscape, and that's something that we have to take into account. So in order to overcome this, Dries has done quite an elegant thing. So he actually, he started with, let's say, a very simple kind of specific example. Let's say, let's take actual molecules, right, which are basically molecules that metabolites from human serum. And then, okay, we know the NMR spectrum, and then he asked the question, can we cluster them, right? And indeed, so he used a variety of clustering algorithms. So obviously, in order to define how close different clusters are, you have to define the distance, right? So again, this A is really this A of omega, right? It's really this NMR spectrum, right? And then there are several natural ways to define the distance. It appears that Hellinger distance, which is defined in this way, and I remind you that the spectrum is a positive number, right? So the spectrum is always positive, definite at all frequencies. So it's like probability distribution function, and that's why it's very easy to connect, between the classical kind of statistics, where they work with positive probability distribution function and spectral functions. But anyway, so if you use Hellinger distance, you see that the spectra, they cluster kind of very naturally into 4 groups. And later on, we will discuss that it's not accidental. Actually, it turns out that these molecules, they come in sort of 4 broad classes. And so these clusters actually reflect strong similarities of the chemical composition. And and this realization of clustering is very important. So it turns out that if we start with a completely random initial spin Hamiltonian, and then we try to optimize parameters, as we said, we get stuck. However, if we do this clustering exercise first, and when given a new spectrum, we will ask to which cluster does it belong. So then if we start from kind of the average spectrum of this cluster, we're already sufficiently close, and then we do not get trapped in the local minimum. So then one can achieve the convergence. So therefore, one needs this bit of classical machine learning in order to actually already start in sufficiently close to the actual spectrum. And this will allow NMR inference. Okay, so previously, I showed you a result of just taking all the spectra and doing clustering on the spectra. So obviously you can say, oh, how robust this procedure is. So you can use, say, just part, basically like half of your spectra to do the clustering. Then you take a new spectrum and ask, well, can you see that it actually very clearly we can clearly identify to which cluster it belongs, and you can see that yes, I mean we can very easily resolve kind of see separation between the clusters, and you can also see. So this is a table of sort of like typical distances between spectra in different clusters, and this is what I advertised before. So again, these 4 clusters they are not kind of the fact that the spectra sort of grouped together is not accidental. Say in these types of cluster, you can see that we have few peaks, which means that many of them are multiply degenerate, and this turns out to be that because all the molecules have the special methyl group, right? And you see that these 3 hydrogen are obviously equivalent to each other, or let's say this particular kind of massive spectrum, they all come from molecules in which kind of the proton atoms look a system which is kind of like, a spin chain, right? Of which you would expect sort of the least amount of degeneracies. or again, like so then like when you have some symmetries in the molecule, usually it immediately shows up right in the symmetries of the spectrum. Okay, so that was one aspect of sort of classical machine learning, but actually there was another crucial step that was needed. So it turns out that simple gradient descent was not super efficient, and roughly you can see it from the following arguments. So see, when you do optimization, right, so you have a landscape when it's very rough, right? And it turns out that it happens to have shallow directions. Again, it's something that, okay, we can philosophically speculate why, like all them, like it's not typical if we take a random spin Hamiltonian, basically the spectrum will change quite dramatically regardless of how we change parameters. But when we take molecules which are relevant, which act Hamiltonian, which correspond to actual biological molecules, they always have some shallow directions. Basically, there are certain directions of changes in the Hamiltonian for which the spectrum just doesn't change so much. And that's what makes optimization problem so hard, because when we compute the spectrum, we have a limited amount of resources. We always have quantum noise, right? Remember, it's quantum mechanics. When you run a circuit, right, you collapse a wave function, right? So if you do a finite number of measurements, there is always short noise. So as a result, basically, if the spectrum that you get, you don't calculate exactly, there is always noise. And if you have shallow directions, then this noise actually means that it can very easily exceed the actual gradient, right, in this shallow direction. And that's why simple gradient descent doesn't work so efficiently. So somehow you have to, it's more important to sort of sample, to do something which is more non-local with respect to the kind of, where we say that, well, we want to probe some vicinity of parameters in order to understand in which direction we should move. And so this is something that Dries implemented using idea of Bayesian inference. Again, I will not go into details, but roughly the idea is that, so there is this general Bayesian interpretation of probability theory, which says, okay, let's say we have some measurements, right? In our case, these are spectra. So we have spectral functions, a function of omega. And so given the knowledge of the spectral function, we want to tell something about the distribution function of parameters. Like in our case, what's the probability distribution of, like what can we tell for the values of these j's? And now I say, well, let's say they're probabilistic and we assign a certain distribution function to the values of these parameters. And then we can write a simple conditional probability. So what is the value of having certain parameters theta, given that we had certain measurements of the spectral function, right? And this is just the usual sort of rule of conditional probability. And you can work with, starting from this, you can actually develop a very simple procedure which allows to make an update, that you start with some initial prior belief of what your distribution function of parameter was. And then you take new data, right? You measure more spectrum. And based on that, you can then update your kind of belief, like you can get a more accurate probability distribution functions of theta. And this theta, remind you, these are J's and H's, right? And then the trick was that, okay, in principle, one can sort of do this distribution function exactly, but what was more efficient was to just assume that the probability distribution functions were Gaussians. And therefore, as we take more measurements, for these distribution functions of parameters, we just have to update the average values and the covariances. And so with this kind of Bayesian model of the distribution function, like you can see that the procedure converges quite rapidly, so like in the number of steps of the order of 60, and this is we converge sufficiently closely to the actual value of the Hamiltonian, and how close we converge is actually determined by resources. Like in our case, we sort of assumed a certain limitation on how many measurements you can make, sort of what is basically a quantum resource. So like if you sort of willing to do more measurements, then you can determine the Hamiltonian more accurately. Okay, so now sort of I started by saying that I believe that this is something that can be practically implemented. So let me then comment on some practical aspects. So when we talk about molecules relevant to metabolomics, we talk about like spin Hamiltonians with just 20 spins. And as you can see, the kind of the number of qubits which we needed to implement this was basically sort of twice larger, right? And like even quantum supremacy was already done with more than 50 qubits, right? So therefore, again, this is kind of a perfect problem for this type of devices which have a limited number of qubits. Another concern you can have, okay, but let us think about energy scale. So the width of, like how accurately do we have to implement the gates, right? Because we know that our computers are not perfect. And at first this sounds scary, right? We said that NMR is operating in megahertz scales, and the width of individual peaks is just 1 hertz. But what we should remember is that most of this megahertz is just this very boring, Zeeman energy of a bare proton. So the relevant energy scales for us is really just the differences of Zeeman energies and the typical interactions between the spins. And the scale of those is just 10 hertz. So therefore, we really have to simulate, we have to understand the Hamiltonians in which the decoherence rate is of the order of 1/10 of the parameters. Therefore, it doesn't make sense to actually use quantum computers, which are more accurate than this intrinsic noise of the quantum system, which we are trying to understand. So from this point of view, like the current decoherence rate should be well in line, should be reasonable for actually modeling this NMR spectrum. And then in terms of like, is it a problem that's actually relevant? Well, we're talking about kind of real world problems. So there is an actual, like metabolomics is an actual market, right? Which is valued in billions of dollars per year and which is growing quite substantially. And as I said early on, like a lot of this field would get a dramatic boost if interpretation of an NMR spectrum could be improved. And I think this is where this kind of quantum technology can make a quite important contribution already with the tools that we have available now. Okay, so now what about just a few words about actual hardware. So I'll just comment on like issues. Okay, so as I said, you have to have interactions which in principle are long range. Okay, can you do this? Well, actually for ion qubits, that's exactly what they can realize. So they can have chains, very long chains, but by entangling spin qubits with the transverse phonons, they have already demonstrated that they can have qubit operations on any arbitrary pair of spins. So this was done in Chris Monroe's group recently. So perhaps one aspect which is more subtle is, all hardware only has its own natural gate. So when we talk again about ion qubits, the natural gate is sigma x, sigma x. But what we want to implement is SU2 symmetric interaction, right? It's this Heisenberg Hamiltonian. So, by itself, so we have to actually do extra work in order to understand how to represent this evolution with the Heisenberg Hamiltonian, given the natural gate with ion-based quantum computer. Well, the idea is very simple, that we have to do tritorization. We have to break evolution into many steps. And then every step, right, we can write as, let's say, evolution of Sx, Sy, Sy. But then if we want to, so Sx, it's very easy to implement as a gate. But to do Sy, for example, we have to combine single qubit rotation with sigma xx, right? We sort of rotate yy to xx, we do xx gate, and we rotate xx back to yy, right? And so on. And that actually, again, brings up an interesting optimization problem because, so to minimize tritorization error, then you want to actually make this kind of step as small as possible, right? But that will come with a price, because if you do this, you have to apply many operations, and it turns out that for ions, sort of, well, every operation, regardless of the phase, takes the same time. And on the other hand, they have just heating due to longitudinal phonons. So after a certain number of gates, your just gates become very imprecise. And therefore, there is a certain optimum number of tractorization that you can find in which, let's say, you do not get a perfect tractorization error, yet your implementation is still accurate enough so that, you know, towards, you do not have to make so many operations that toward the end of your cycle, you know, your operations become very inaccurate. So you actually have to find the right balance. And again, if you have to look at the numbers, and what you find is that it seems like with current hardware, it's very realistic to do this NMR inference with molecules of a few, like 4 to 6 spins, already with systems that they have in the lab, and with sort of reasonable improvements, which we can expect in the next 2 years, then they should be able to do this inference for larger systems of, let's say, 20 spins, which are needed for actual metabolomics. Okay, so I focused on ion-based systems. Again, for superconductors, the concern can be, well, okay, let's see, if we think about these devices which were used to demonstrate quantum supremacy, they really just allow nearest neighbor interaction. So in this case, how do we even implement kind of longer ranged interaction? So that again is something that you can overcome using ancilla. I'll just give a very simple example. Say we imagine that for some reason I wanted to implement interaction between 1 and 2, not directly, but through some ancilla. So now, again, let me just use a simple example. I have sigma x, right, between my qubit 1 and ancilla, qubit 2 and ancilla, right? So then you can see that if I start with qubit, this ancilla qubit b, it's strongly detuned, I can effectively integrate it out, and I will get effective interaction between 1 and 2. So of course, like for 2 qubits, it's not clear why you would like to do it, but now you can see that, oh, but then this is an efficient way of introducing safe interaction between all qubits 1, 2, and 3 through ancilla, right? And then we can add even more. So in particular, if we want to study this, like again, this 4-spin module that I told you before, actually you can implement it using the qubit device, which is currently available at IBM, that has 5 qubits and only has these kind of nearest neighbor interactions. Okay, and then one can show that you can generalize it to even longer range using some kind of non-local, using some kind of bus, let's say resonator line, which allow to couple at longer distances. Okay, so how much time? Wow, I actually guess I'm already out of time. I guess I didn't appreciate. Okay, so Adrian, so what's the plan? So should I just stop here?
How much time do you need? I don't think people will complain if you go a little bit over time. So
okay, so
how many slides do you have?
Probably it will probably be like 10 more minutes.
All right, sounds good.
Okay, so now let me change gears. So now I sort of come back to more familiar terrain for us who do many-body physics, and let's talk about the Fermi Hubbard model, and that's how we can get new insights from quantum gas microscopes. Just to remind to non-experts that when we talk about say strongly correlated electron systems, there is a paradigmatic model, the Fermi Hubbard model, which is believed to be at the heart of high-temperature superconductors, that can be realized using fermions and optical lattices. And then there is also a close relative of this model, the so-called TJ model. And what has been kind of a game changer in the last few years is development of quantum gas microscopes, which allow to measure all particles at once. So it's really like it gives this tool gives us snapshots of many-body wave functions. So we can start discussing many-body states beyond the paradigm of 2-point correlation functions. And one of the striking manifestations of this was the work by Manuel Bloch, and as I understand, he's coming next week, and so he'll tell you about the experiments in which they measure magnetic polarons. So it's a doped Fermi Hubbard model, and then they ask, so how magnetic correlations are affected by the presence of a mobile particle. In this case, it's a doublet, and these changes can be quite dramatic. Say this next nearest neighbor diagonal correlations can change from being ferromagnetic in a Mott insulated to being anti-ferromagnetic when they are next to a moving doublet, to an itinerant doublet. Okay, but there is something particularly interesting about the motion of holes like quadruplets and in these Mott insulators, and this is that when they move, let's just do this very simple exercise. You see, we started with a hole in a perfect antiferromagnet, then it moves. You see that it leaves behind a string of flipped spins, right? And that is kind of shows you, and that's why people said that it's reminiscent of spin charge separation in 1D. However, the spinon and holon are not completely free from each other. Like in 1D, they can just separate and move independently. Here, they're connected by a string. So we get a picture which is very similar to quarks connected by a string in QCD, right? And that's the picture of mesons, right? So basically, there is a linear potential when we try to separate two quarks. And the question you can ask, can we use quantum gas microscopes to actually see the strings? So if we take a snapshot, right? So if there was a hole, we will see that as a hole moves, right? You see it leaves behind these strings. You see here that there was this frustrated bonds, right? Which was nearest neighbor was supposed to be antiferromagnetically coordinated, but actually here you can see that correlations become ferromagnetic. So can they be measured? And so this is like something that Marcus Greiner's group set out to measure. So one thing, however, that turns out that the limitation of Marcus's experiments is that so they have the coldest temperatures. However, the price at the moment that they pay is that they cannot resolve simultaneously spin up and spin down. So it's different, say, from Emmanuel Bloch's group. So they can actually measure spin up and spin down in the same image, right? So that's why they were able to see, this magnetic correlation around the hole. But in this case, it turns out that this is not, okay, so that's a limitation, but it's not a showstopper. So you can still adjust the procedure to take this into account. But roughly the procedure looks as follows. So, okay, so imagine that we have a system, right, which is, okay, it's a schematic representation of the Fermi Hubbard model, right? Red and blue are spin up and spin down particles. And now on one side, we can have both of them, or we can have none. And so experimentally, they have to choose either the image just all the blue, but if the image blue, then let's say doublets will show up as empty sites, right? So kind of both empty sites and doublets will show up as empty, and the red ones will also show up as empty. And also, like if they choose to image red, they would just see red, and then blue, doublets, and empty, they would show up as empty. So let's say if they choose to measure blue, okay, so what they will see is that they will see something that still has some resemblance of checkerboard order, right? Because we're not too far from antiferromagnetic state, but it's not perfect, right? So here, then what you can do, you can find the best optimal checkerboard configuration, right? And then you can ask, okay, so what is the difference between this closest checkerboard and configuration that we actually have in an image? And let's see what the difference is. Okay, and so here you can see that the difference includes a collection of, let's say, 4 flipped sites. Here we have 2 flipped sites, another pair, and just 1. Then we can plot the distribution. So these are our strings, right? And the strings can come literally from the strings because of the hole propagation, or it can come from the fact that we had doublets, or from the fact that we had holes. Unfortunately, here they are all combined together. And then, okay, so let me skip. Since we don't have time, just to give some disclaimers that, okay, like you should be careful that because our quantum antiferromagnet, right, has some flip-flop, right? It's not a classical antiferromagnet. So even if we take a half-doped system, we will already get some strings, and they come from quantum fluctuations, from thermal fluctuations. So it's kind of a background. But what we are interested in is the excess, is actually what is the increase in the number of strings that we get from adding holes. And you see that this is, so this was a distribution at half filling, and then when we add holes, the number goes up. And okay, notice it's logarithmic scale. So this is like for longer strings, it's almost a factor of 10 in the probability of longer strings. You can say, oh, perhaps this is just because we added some holes. Well, you can just add some, sorry, I'm going the wrong direction. You can just sprinkle some holes, and you will see that the increase in the strings just due to random addition of holes would be much smaller than the one that was seen experimentally. So we can really see that these additional strings, they come from the whole motion actually introducing frustration, introducing the kind of frustrated bonds. Okay, and this just shows you, let's say, the probability of having just a string as a function of doping. So this is a probability of having a string that we started with at half filling, right? Because already at half filling, we said we have some strings, and then it grows up. And if we simply edit holes, we would get a much smaller increase. And okay, what I don't have time to describe is that one can actually develop a fairly simple model, which is really takes this picture quite seriously of a spin and holon confined by a linear potential and moving in configurational space. And that provides a fairly good description of the distribution function of strings. And okay, but so the last idea that I want to mention is, I already said that what we are getting from working with the quantum gas microscopes is images, right? And we know that kind of machine learning is very good in sort of doing identification of images, right? They can distinguish, like neural networks can distinguish cats from dogs. So now we can ask, well, can we use the same ideas to distinguish different types of theoretical models? So in particular, what we did was to choose two models. One is conventional spin liquid type RVB theory, which is a kind of like it's mean field theory, but geared not towards antiphonognetic state, but rather spin liquid state. And the other, and that actually sort of treats correlations between, in a sense, kind of change of magnetic correlation used by holes on a more mean field level. And the other is more this kind of geometrical string where we say that, oh, as a holon moves, it reshuffles around the spin configurations. And so we can use both of the theories to generate images just the same way as kind of the same snapshots as we get from experiments. And then we can ask, okay, so can we use neural networks to tell us which of the theory, like which of the two theories provides a better description of the experimental data? And so this is the work done by Annabelle. And so she came up with two very interesting, and Fabian, so two of them came up with two very interesting ideas. So one is to actually, okay, we have three types of images. One is experiment, and then two theories. And then you train your neural networks on these three types of data. And then you bring new images, and then you ask, okay, is the theory, how well can I distinguish the three classes? And it turns out that experimental, that these neural networks can very easily distinguish these pi flux models, RVB pi flux, from experimental data and from geometrical strings. However, it's very often, like the neural network is very confused. So geometrical strings and experimental data look extremely similar, which suggests that, yes, the geometrical string is actually a closer representation of the data. Another thing that they have tried was to actually train the system just on theory data. So at the training stage, neural network has never seen experimental data. And then it was trained on these two theories. And then you bring in experimental data and ask neural network to assign it either to the RVB theory or to the geometrical string model. And you can see that like up to at least 15% doping, it predominantly assigns experimental data to geometrical string. And it may seem like, okay, so this probability difference of you know, okay, so here we're also talking about those order of 15% for a single snapshot. It doesn't look so convincing, but you should remember a single snapshot is a very limited field of view. It's like, you know, 9 by 9. So if we give several snapshots and we say, oh, all of the snapshots come from the same class, then immediately say the probability of assignment to a specific theoretical model goes to 80%. So this, again, here we see that, again, this geometrical string model, which really takes into account local rearrangement of spin correlations around the hole, provides a much better description of experimental data than these kind of simple kind of RVB or just generally mean field type wave functions that we are used to. Okay, so with this, let me conclude. So I try to give you a couple of examples where I think we can get very interesting new ideas and new results by combining quantum simulators with classical machine learning. So I'll talk about quantum-assisted NMR inference, which I think is a very promising potential application of quantum technologies to the real-world problems. And I also talked about how we can get new insights into the Fermi Hubbard models from quantum gas microscopes. Thank you, and I apologize for being over time.
Thank you, Eugene. You know, we have to get used to not having an applause at the end of the talk, but I think the audience is really excited to learn about your project. And now I'm going to open the session for questions. So I'm going to ask the audience to raise their hands if they have any questions, or to post the questions on the chat box, and I will read it to Eugene. Celso has a question. Please, Celso.
So Celso, I think you're muted.
Yeah. Yeah. Okay. When you talking about this caffeine, you yes, in the this is in the very beginning, you have used several, I'd say several metrics to make this clusterization of the structure, right?
Yes.
My question is the follow. I saw there probably 3 metrics, but there is one that is, I think this is the best one. Mm-hmm. I don't remember the name. I want to know how. Yes, exactly. Yeah. How do you know to choose? I mean, what do you do to choose the right metric for clustering? You have just to try.
So Franco, I mean, we were just practical. We tried like all 4 of them. We saw the one which works clearly, sort of gives a cleaner separation between the clusters. So we did not try to turn it to an actual kind of, I don't know, machine learning problem. What is the most efficient algorithm?
Yeah, because here, for example, you have this Euclidean distance. You could guess, okay, here we don't have just 4. We have, I'd say, 6 or 7, right? And this is the same for this Jensen-Shannon distance. Yeah, but okay.
Well, Jensen-Shannon seems to be 4. So somehow, I mean, we noticed this, the Jensen-Shannon and Hellinger, they gave roughly the same clusters. And that's why we started with 4. Okay, so here you can say we had the benefit of hindsight that, okay, like in the case of this 4, it turns out that, that there is actual chemistry behind it.
Yeah, sure.
But so generally, it just looked like, okay, these 4 clusters seemed more robust across different measures.
Okay. Thanks so much. Thanks for your talk. It was really, really interesting.
Thank you.
I'm sorry, I was muted. My kids were screaming. So thank you, Celso, for your question. I just read one from the chat. Igal Mayer is asking, in the ion trap qubits, how do you control the different long range couplings, the exchange JIJs?
So this is basically by, because what you do, you entangle spin qubits with the phonons, and phonons operate through the entire chain. And that's why if you sort of couple to the appropriate phonon, you can get the kind of, by choosing the correct detuning, you can make sure that you couple appropriately, like you excite the appropriate phonons to have specific coupling to an ion, like which, you know, because you know specific matrix elements of the ions to these phonons. So that's kind of an answer in a nutshell, because you're involving degrees of freedom, phonons which sort of operate inside the entire chain. And that's something that, again, it's no longer just theoretical proposal, but that's what has been demonstrated experimentally.
All right, any other questions from the audience? I have one. So this idea of whole motion leaving strings behind comes, you know, it's pretty old. It becomes exact or quasi-exact in the limit of you know, strong Ising anisotropy in the TJZ model. But you know, people have argued for a while that in the Hubbard model, the spin fluctuations and the Trugman paths would basically erase the strings. So what we are seeing here in the experiments is that basically these strings are actually long-lived and they're not so easily erased.
So what we see is that they provide a fairly useful way of describing the actual, let's say, spin correlation. So this is a part which, okay, I didn't have. Maybe I can show it now. So how would you describe, let's say, the change of spin correlations around the hole? So the model that I gave of the string is basically to say that as a hole, like this holon moves away from the spin and it leaves behind the string. But also, if we want to represent this dynamics, right? So then what we have to do is we have to remember, we can set up a tight binding model. However, the tight binding model for a hole is not just, you know, we do not just label the instantaneous position of the hole, but we have to specify the entire trajectory. Because when as a hole moves, right, the string is left behind. So we can distinguish different paths by which a hole arrives at a final point. And that's why you can think about this model as basically kind of like a tight binding model on a beta line.
It looks like we lost Eugene. Crisia, we lost Eugene?
We lost him, yes.
Yeah. All right, let's see if he comes back in the next. Oh, Eugene is back. All right. Please, Eugene, unmute yourself and continue. You can share your screen with us.
Yes. Yeah. Oh, I have to share it again. Yes. Right. Okay. Sorry about that. I guess I lost you when I was explaining that this model of exponent holon separated by a string can be converted into a tight binding mode on a beta lattice where we label all configurations. And this can be used to make predictions about the spectrum, right? That's what people have done before. But now what we can also do is we can make predictions about correlation functions. So this, hopefully you will see, let's say in the manual blocks data, that like we can look at how, let's say, nearest neighbor, next nearest neighbor correlations are affected by the whole. And so what we have seen so far is that from all the theoretical models, this kind of meson-like picture gives the best description. And it's not only equilibrium, but say like recently, Marcus Greiner's group, they also looked at dynamics. They had a confined hole and then they let it go. And as a hole propagates, it starts messing up, you know, just by, again, so you have a holon which moves fast, and as it moves around, it also changes spin configurations. And you can separately keep track of how magnetic correlations change and how the hole expands. And so interestingly, this simple model, which Adrian kind of in a sense, as you said, theorists kind of dismissed because, I mean, the reason why we dismissed it is because, well, not us, but let's say previous generations, because it did not have a well-defined small parameter. It's not like BCS theory, where I can prove you that it works exactly. But from the practical point of view, if I want to describe experiments, it works remarkably well. So that's kind of the practical lesson that we learned so far, that at small doping concentrations, again, like small, like at this point, it seems like it's around 15%. Also, what perhaps works for us is the temperatures are not so low. You see, at sufficiently low temperatures, clearly holes will have to start self-organizing. It may be D-wave pairing, it may be stripes. So then these arguments will probably not apply. But at least in the temperatures relevant to current experiments, where sort of these polarons live more or less independently, this seems like an excellent description. So if you want, you can call it phenomenological model. So does it answer your question?
Yes, yes. Yeah, but rather than phenomenological, also, I mean, the fact that in the experiments you can see the traces of the strings means that they're physical, right?
Yes.
So, but I don't want to take too much time. So I'm gonna read to you one last question from the chat by Xin Zhang. And the question is, if the neural network captures the two theories and can tell you which one is, you know, more closer to the experiment, in the case of the cold gas, can you extract information about the signatures learned by the neural network? I suppose what the question means is that
interpretation.
Can you figure out what what distinguishes each theory from each other? I suppose
we believe we can actually. So I think so. We're working on a paper with Una Kim's group. So and we will have we have the results. But since I don't have the permission of my collaborators to discuss them, I'll just say that yes, we can learn what the neural networks find, and we'll have a paper on this soon.
All right, very good. Looking forward to it. All right, we have no more questions. I don't see any hands raised. So let's thank Eugene one more time. Thank you for being here and sharing your work. And thank you all for joining us today. And looking forward to our next meeting next Monday with Emmanuel Bloch. Thank you very much.
Well, thanks for the invitation. It was a pleasure. Thank you for the questions.